Hello students, welcome to this introduction in system identification or subspace system identification of deterministic systems. That is systems where we also have known inputs in a vector U influencing open the output. Here I have started with an autonomous system. That is a system with only outputs. And the system is dynamic with a given state vector x, described by such a state space model, linear state space model. Then there is an initial non-zero state vector, x0, which are influencing open the output, like this. From this we derived first one matrix equation, this equation 1 here, where this data matrix Y is equal to the product of the extended observability matrix O times a vector X with states, like this, where this state X0 equal to a matrix. It's the initial state X0, X1, X2, like this. And we can also develop a second matrix equation, this equation 2, called Y1 given L equal to a matrix A L tilde times this Hankel matrix Y0 given L, this one. A proof of this one given as follows. Yeah. You see, suppose that instead of developing this one at starting point x k equal to 0, we may define, similar to this one, we can define y1 given L equal to the product of the extended observability matrix OL times a matrix with states x1. This one is very exactly similar to this one, but starting at k equal to 1. Oh. And you see this using this state equation xk plus 1 equal to axk. We also have that this matrix x1 is equal to, using this one, is simply equal to a x0 with this definition, and where x1 is simply state at time 1, at time 2, and so on. Putting this one into this equation gives OL a x0. And remember, this x0 can be calculated from this equation 1. Of course, if this extended observability matrix is square and invertible, we can multiply from left with the inverse of this one to obtain x0 alone. But in general, this OL is rectangular. So let me multiply this one with OL transpose first. Then we have OL by 0 given L goes equal to a square n by n and invertible matrix, like this. This one may be solved for x0. The inverse of OL transpose, OL inverse times OL transpose times Y0 given L. In fact, this matrix is the so-called Moore-Penrose pseudo-inverse of the matrix OL. I very often define OL plus as this one. Defined as this pseudo-inverse. OL transpose, OL inverse, OL transpose, Y0 given L. Now we can put this equation into this one. Or here. So equation 1, 2, I use a number here. Equation 3 and 4. Putting 4 into 3. And we have that Y1 given L is equal to, I have used the definition AL tilde Y0 given L, where is A tilde L matrix is this rectangular observability matrix OL times A times the pseudo-inverse OL plus, or simply OL transpose OL inverse OL transpose. Yeah, times Y0 given L. Okay, students, all this can be extended to a so-called deterministic system. That is a system where we, in addition to this unknown initial state vector x0 influencing open the output, have a known input vector uk also influencing open the output. So given a deterministic like this. This system is dynamic, so we have an internal state vector x taking care of the dynamic behavior from the inputs in vector uk. This one, remember, this one is an r-dimensional vector. So this one and the non-zero initial state vector x0 are influencing open the output, which is assumed to be m-dimensional. And given data observations. Observations. UK and YK for all discrete time instance K from time 0, and we assume uppercase N known data dot 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 up to N minus 1 then. Very similar to the autonomous system, we may deduce some matrix equations. But of course, we have to assume the structure of this model describing this deterministic system. Oh. And it makes sense to assume a linear, discrete time state space model of this type. But since we have known inputs, we may have an additional term in the state equation. So we assume. By a state space, the state equation xk plus 1 equal to axk plus buk. And we also assume a possibly non-zero initial state vector, an unknown. Non-zero initial state vector. And the output equation equal to dxk. But since we have inputs, there may sometimes, due to sampling, be a direct feed-through term in the output equation this time. Sometimes. Not always. So, in order to simplify the identification problem, is to, from those known data, identify the system order n and the model matrices. Equation 5 for the data from known in 5, identify dot the system order and the four matrices A, B, C, and E. And I write and or. And the reason is that I will now include a so-called structure parameter. You see, this direct feed-through term from the input to the output is a rare property. Because you see, in dynamic systems, there will very seldom be direct momentaneous influence from the input U to the output. But due to sampling, as I said, we may have this term. So I will include a structure parameter. This is a definition. Define a structure parameter. I will use G, lowercase g, for this one. If we put G equal to 0, then we assume that this term is 0, that E matrix is 0. So we don't, in that case, don't have to identify the direct feed-through matrix E. So G is equal to 0 when we assume that E is equal to 0. The other case is to estimate E. That is, that we assume that there is a direct feed-through term from the input U to the output. When E is not equal to 0, that means that we estimate to have this structure parameter in mind. Now I will write up two important matrix equations in connection with the so-called deterministic system, which is an extension of those two matrix equations. You see here, we have that the output matrix, Hankel matrix Y0 given L is equal to the product of the observability and the state vector matrix X0. So, since we have additional inputs here, we will have a second term here. Oh, matrix equations. We have Y0 given L equal to the product of the extended observability matrix OL times X0. But since we have inputs U, we have a second term. Also equal to the product of a matrix HL. I use D. This D is to indicate the deterministic. And L means the number of block rows in this H matrix times a Hankel matrix defined from the known inputs starting at time 0 given L plus G minus 1 rows, where so I will use equation 6 on this one. This one can be deduced very similar as we deduced this one. But the difference is this so-called Toeplitz matrix H. HLD. A matrix like this, consisting of impulse response matrices. Remember the impulse response matrices is E, EB, DAB, dot, 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 up to D in A I minus 1 times B. This is the impulse response matrices of the system. This one, the first row here is E here and DB and DAB, dot, 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 down to D in A L minus 2B. Sorry for the back. Okay, students. Unfortunately, I have a tendency to touch this one. Let me finish the definition of this matrix H. The second row, I have 0 here, and E on the block diagonal, and DB here, down to DA in L minus 3B then. Dot, and 0 here, dot, and E in the lower right corner. This is the case where when the structure parameter G is equal to 1. So let me open this one. Let me take some examples. 2 examples. Put say L equal to 3, and this structure parameter equal to 1. As an example 1. And the problem is to define this so-called two-applets matrix. A two-applets matrix has this special structure. The diagonals is the same. So then I will define H3D. And we have 3 block rows, E here, DB, and DA times B. And 0, E, DB. And in the third row, 0, 0, E. Let us take an example, a second example where G, the structure parameter, is equal to 0. That is, that we don't want to estimate E. Here I still want L equal to 3, but this structure parameter 0 means that E is 0. Then we have H3D. Then we have 0 up here, DB, and DAB, and 0, 0, DB. And since E is 0, we skip the last block row. So this one will have a lower dimension. Remember this. When G is equal to 0, the last block row in this matrix HLD goes away. We have also here very similar to this second matrix equation in connection with the autonomous system. We can deduce a second matrix equation for this deterministic problem. So we have this matrix equation and second matrix this one reads y1 given L equal to AL tilde times y0 given L. But since we have non-zero inputs U, we have a second term here. I use BL tilde for this matrix. I'm Hankel matrix defined from the non-zero input. U0 given L plus G rows. Here we have L plus G minus 1 rows. Where this AL tilde is exactly the same as we deduced for the autonomous system, equal to the product of OL times A and the pseudo-inverse of OL. I can simply write OL plus for the pseudo-inverse. But remember, this pseudo-inverse is like this. OLA times the inverse of OL transpose, OL inverse times OL transpose. This is AL tilde, but what about this B tilde? This BL tilde is a matrix like this. OL times B here, and this HLD matrix minus a matrix with AL tilde times a matrix of same size as this one, but HLD here and a matrix with zeros here. You see, this zero matrix at the end here would have the same rows as this one. And remember, the number of rows here is L times M. LM. I need some space here to define this one. LM by R. The number of columns in this one is R. Equation 6 is this one, and 7 then. The proof of this one follows the same lines as I proved the corresponding matrix equation for the autonomous case. So, summing up. In connection with a deterministic system, we have two matrix equations. First one, Y0 given L equal to the product of observability matrix times a matrix with states plus a Toeplitz matrix defined from the impulse response matrices, starting at time k and having L plus this structure parameter G minus 1 rows. And the second matrix equation is this one. Remember how to find the system order now. It is in fact from those two matrix equations. Remember back to the autonomous case. It didn't have this second term. So we simply calculate a singular value decomposition of this one. And we find the system order as the number of non-zero singular values of this one. And we estimated OL and X0 in our first step. So now, the next now is to look for a projection matrix. Suppose that we can multiply this equation with a matrix which is zeroing out this term and not destroying the information about system order. And then we need theory about orthogonal projections. I search now for a projection, so such a projection matrix. Look here, search. A projection matrix. Say P. Search that. If we multiply this equation from right with this, at this stage, unknown matrix P, I have Y0 given L times a matrix P equal to OL times this X0 times P only. And this matrix U0 given L plus G minus 1 times P equal to 0. This is the point with this projection matrix P. And since this Hankel matrix Y0 given L is known and P is known, then we can calculate this one. I have defined the result as a set 0 given L. And then we can use our singular value theory, taking the singular value decomposition of this one, and estimate the system order N and the observability matrix OL. But orthogonal projections will be the topic of a separate lecture. Thank you, students.